Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tear. This is my continuing feature on the Math Lovers book. And as I do every Saturday, I'm featuring another biography of a famous mathematician. I have these listed at the end of volume 2, the green volume in the middle here. Um, I have the bios of 80 famous mathematicians throughout history listed chronologically. And today I'm up to the 26th of those, and that one is Brook Taylor, who lived from 1685 to 1731. Here's a picture of him, and here's my bio of him that I feature in my book. And he really had one result, one main result that he's famous for. It's known as Taylor's theorem, or equivalently the Taylor series. And that's a formula in the middle of this slide. I actually have some other slides that show it better. So there's something called the Taylor series, a very, very useful series. It's this thing on the top of the slide shown in yellow. So what it is if you have what's called an analytic function, which most functions we study are, it just means that it's arbitrarily differentiable. And if you don't know calculus, don't worry about that. You kind of have to know calculus to understand what Taylor series are, Taylor's theorem. But as long as you can calculate arbitrarily many derivatives of f of x, that's just another way to say that it's analytic, but at least at some fixed point, which you usually call a. Then what we can do is we can make what's called a Taylor series or a Taylor expansion of f of x about x equals a. And the reason this is useful is because it gives you a really nice way to approximate most well-behaved functions, analytic functions anyway. You can use a series to approximate the value of f of x at any value of x near some starting value, which we're calling a. And this is used on calculators. I think all the scientific functions that calculators use, like square roots, nth roots, as well as trig functions, exponential, logarithmic functions. All of these have well-known Taylor series, and you can apply the Taylor series formulas for these functions to calculate their values at any value of x you want, pretty much. I even kind of know how to do this in my head, at least to about 3 decimal places. I do have a video where I kind of show how to be a human calculator. And I think the last one I did was I showed how I could calculate some Taylor series in my head. And Richard Feynman was another person who was able to do this, and he impressed a lot of people with it. But usually this is done with calculators or computers, and the part in blue on this slide just shows you some specific examples of Taylor series, and they're also if the expansion if we have a equals 0, which is the most common case, that just means we're expanding our function about x equals 0. Then it's called a Maclaurin series. A Maclaurin series is nothing but a special case of a Taylor series. And on the bottom, this is what we usually use. And here's some examples of some common Maclaurin series you'll see a lot. E to the x, that's the first one, exponential function, has a nice simple form, just the sum of x to the n over n factorial. And then sine and cosine are kind of closely related, it turns out. These also have rapidly converging Taylor series. And another one that's commonly used is 1 over 1 minus x. That's just a geometric series. That turns out to be just the powers of x to the n. So 1 plus x squared plus x cubed, so on. Anyway, those are some simple examples of Taylor series. And there's a lot more, and they're easy to calculate if you don't know them. And they say a picture's worth 1,000 words. So here's a graph of the first. I think it's the first 7 terms in the Taylor series of the sine function, sine of x. And the first term is just x. That's the red line here. Whenever you go to order 1, you get a line. And this is actually the line that best fits the sine function about x equals 0. It has the same slope as sine x, namely 1. So this is the slope of, it's just a line passing through the origin of the slope 1, y equals x. Not a very good approximation of sine x, but sine x is approximately equal to x when x is small. You might have learned that when you were first learning calculus. And you can add more terms if you want better and better approximations. So I think the orange one is a cubic approximation, x minus x cubed over 6, I believe. And you can keep adding terms. I think the next one's a green one, then the blue one, and I think the purple one is the most has the most terms. That has, I think, 7 terms. That goes up to like x to the 15th because you only have the odd exponents with sine. You'll notice something interesting about these pictures. They're very they get very close to the sine wave near the origin, but the farther you get out from the origin, the worse they get. That's true for all of them. And even the one with 7 terms, it was a really excellent approximation near the origin. If you get too far away from the origin, it blows up. These all blow up because these are all polynomials. The sine wave is not a polynomial. It's well behaved. It's bounded by y equals plus or minus 1. But polynomials, no matter how big their degree, they all blow up if the absolute value of x gets large enough. They go to plus or minus infinity. So you're always gonna, you always have kind of a limited region by which the Taylor series is a good approximation. And there are other series that do better in this regard, at least. Fourier series. I think I'm going to do Fourier's bio in a few weeks, so I'll talk about Fourier series when I get up to him. Um, but anyway, Taylor series are very useful, like I said. And one very useful, I love this derivation. I think that one of the most, what some people consider Euler's formula, the greatest, the most important formula in math. I think Richard Feynman did, and I kind of think it's the greatest. I mean, I don't know. There's a lot of other mathematical results that are pretty great, like the Pythagorean theorem, and but this one's up there definitely. And what it says is e to the ix is equal to cosine x plus I sine x. Euler discovered this formula in 1748. It tells you how to exponentiate, complex, arguments. You how to, like in this case, if x is real, e to the ix is a pure imaginary. X doesn't even have to be real. X can be anything. But the way you usually learn the derivation of this formula, and don't worry about this if you don't understand it because this requires some calculus. But it turns out you can write down the Taylor series of e to the ix just using the known Taylor series of e to the z. Just like I said, as a sum of z to the n over n factorial, and you just substitute ix for z, and then you take powers of I. Actually, you don't really have to know calculus to understand this derivation. You just have to know what the Taylor series of e to the z cosine z and sine z are. And then what you do is once you simplify this, you separate out the real and imaginary components, and lo and behold, the real component turns out to be the Taylor series for the cosine function, and the imaginary part is the Taylor series for the sine function. And you have a factor of I outside. So you get cosine x plus I sine x. That's how you derive. This is how most students first learn how to derive Euler's formula. So I think it's a really beautiful derivation. Anyway, I think before I finish, I should say one more thing about Taylor series. They don't always work. I mean, most of the time they do, but the function has to be analytic. And the classic example you see of a case where it fails is e to the minus 1 over z squared at z equals 0. And the reason it fails there, even though it is infinitely differentiable at z equals 0, all the derivatives turn out to be 0. So according to if you kind of naively apply Taylor's theorem, which doesn't apply to this case, about z equals 0, you would find that your function e to the minus 1 over z squared is identical equal to 0, which obviously it's not. But the reason it fails is because e to the 1 minus 1 over z squared is not analytic. As a matter of fact, if you used an imaginary value of z, it would go to infinity near the origin. So it doesn't even uniformly. Over the reals, it goes to 0 at a equals 0, but over the complex numbers, it doesn't. But anyway, I just thought I'd mention that. But like I said, Taylor's series are very, very useful. And I think that just that discovery alone by Brook Taylor puts them in the, at least in my list of great mathematicians. So anyway, that concludes my video today. My feature on Brook Taylor. Thank you for watching. And long live math. I'll see you guys next time.